Okay, in the previous sections, we have learned about the conservations of mass. In these sections, we are going to talk about the next material, which is conservations of momentum, which is actually the equations of a Newton's second law. We implement these equations into fluid dynamics problems. Okay. So what is Newton's second law of motions? It is the time rate of change of the linear momentum of the system is equal to the sum of external forces acting on the systems. Okay, so this is when we define the conservations of momentum or the second law of motions in a system framework, we will have this one. So it is the time rate of the momentum will be equal to uh, the total of external forces, or can also the resultant of external forces act on the system. Okay, but like what we have before in conservations of mass, in fluid dynamic we need to arrange the system framework into control volume framework, and then we will have these equations. We will have the control volume and also the control surface, and this will be equal to uh, the, the external forces or the resultant of forces content of the control volume. Okay. Okay, like what we have before in mass conservations, we need to analyze uh, momentum conservations into steady state simplifications. So, as a steady state concept, we don't calculate these equations in the time rate framework. So that's why we will have these equations, or I mean, this is will be equal to zero. So we'll focus on the control surface. So it is the momentum uh, at the inlet of the control volume and also the momentum at the outlet of the control volume. The difference between this momentum will be equal to the resultants or the sum of the forces content of the control volume. So when we integrate these equations, we will have this is the momentum at the outlet and this is the momentum at the inlet. So we will simplify these equations, or we'll have new equations. And you need to, I think you already knew that when we talk mass flow, the equation of the mass flow is equal to rho, density, the area, and the velocity. So when we use these equations into these steady state momentum equations, we will have sorry, we will have these equations. It is the mass flow, and then this is the difference between velocity at the outlet of the control volume and velocity at the inlet of the control volume, and it is will be equal to the sigma of forces or F. Then let's talk about the applications of the linear momentum equations. First, we can use these equations in nozzle case where we convert pressure energy into velocity, and also we can say that it is reaction force on nozzle. And if we have a elbow or pipe bend change in flow directions, so it is the resultant force on pipe. And then, like the example we have before, we can also use the linear momentum equations on a jet unpaid problem when we need to find the impact force will be equal to rate of momentum change. And also, these equations will be beneficial for turbine or palm blade case, where momentum exchange between fluid and blades. We use this to calculate the mechanical work of the turbine or palm blades. Okay, this is the example where we use linear momentum equations. This is the control volume. This is the control volume, and this is the velocity at the inlet, and this is the velocity at the outlet. So the force inside this control volume will be equal to uh, the momentum equations at inlet and the momentum equation at the outlet. The difference momentum equations at the inlet and the momentum equations at the outlet. Another case in turbo machinery, we also can use the momentum at the outlet of the jet. This is the momentum that we can use to produce mechanical work, or because it's resulting the force acting on this blade. Okay, so yes, we can use linear momentum equations for this case. Of course, there are a lot of problems that where we need to solve using linear momentum equations, but I hope based on this schematic, you will understand that applications of linear momentum equations is something that very important to you to understand. And then later I will show you an example of linear momentum. And then the last conservation law in fluid dynamics that we need to understand is the conservations of energy. I need to remind you, actually, you have learned the conservations of mass, and we have learned about the conservations of momentum, and the last one we need to understand, or we are going to learn about conservations of energy. So the conservations of energy, if you take the thermodynamic, you will familiar with the first law of thermodynamics, and it is actually the system or the concept that we use in conservations of energy. So what is it? It is actually you can define it as time rate of increase of the total stored energy of the system is equal to net time rate of energy additions by heat transfer and by work transfer into the system. The thing that you need to remember is heat transfer here and work transfer. I think you are familiar with these equations. The difference normally it is because we use in integrations equations, but this is the energy of the system. So the change of the time rate of increase of the total energy will be equal to heat transfer, and this is work transfer into the system. And like conservations of mass and momentum, we need to change the framework from system framework into control volume framework. So these equations will be like this. We have control volume, so the time rate of the energy inside the control volume, and the control surface, and then we have this one, heat transfer and work transfer. Thing that you need to understand also, the symbol in here is defined based on whether the net work transfer is positive or negative, or sometimes we have the case that the work out of the control volume is bigger than the work come into the control volume. In this case, we will have a negative uh, work transfer. So also the thing with heat transfer, in some cases, we have that the heat transfer come inside the control volume is lower than the heat transfer out of the control volume. So we will have a negative of heat transfer. So that's the thing that you need to understand also. Like uh, like other conservation law, we also need to analyze the energy equations or the conservations of energy into a steady and uniform flow with one entrance and one exit case. So we'll have the equation like this, and then since it is a steady case situations, we don't need to calculate the time rate of the energy change inside of the control volume. We need to focus on this one, and then the heat transfer and the work transfer inside of the control volume. So we'll get these equations, and then if we simplify it, like what I said before, since rho A and V is equal to mass flow, and we will have more simple equations. So it is the mass flow and the energy, and then this heat transfer, and this is work transfer in control volume. And okay, the thing that you need to understand when we talk about E, it is the total energy of a fluid particle per unit mass. Actually, it contains the internal energy, which is U, and also pressure energy, and kinetic energy, and also the last one, potential energy. Okay, so when we put these equations into these steady state equations, you will have these equations. So this is the total energy at the inlet and at the outlet, and this is the heat transfer and the work transfer at the control volume.